Hello, this is Joe Bardwell. In this demonstration, we'll see how an RF CAD designer evaluates a facility and formats AutoCAD drawings to create a three-dimensional model. Into this model, access points and obstructions like freestanding inventory are placed. Then, an accurate RF coverage map is generated. Finally, a set of installer's working plans is created. Everything is detailed in a report that we call the Sweet Spot Predictive Site Survey. The generation of three-dimensional RF predictions can be quite time-consuming. So in this demonstration, we've cut out all of the delays associated with manipulating the RF CAD modeling and simulation software. Things move fairly quickly, but afterwards, if you have any questions, we're at your service to get you the answers. The challenge of RF CAD modeling for a production facility is that a real-world facility contains objects like inventory storage shelves with various levels of inventory, stainless steel tanks or vats, piping, a number of obstructions including conveyor belts, divert gates, things that have to be accurately modeled in the three-dimensional modeling space. One advantage is that varying inventory and production levels can be simulated. Whether there are overhead walkways, mezzanines, catwalks, whatever is in the actual production facility can be created in the three-dimensional RF CAD model. This is the job of the RF engineer. First, the AutoCAD drawing is examined to study the architectural layers and structure of the facility. Then, from a library of construction materials, materials are selected that represent the RF characteristics of the building. If there are materials that we don't have in the library, then an on-site engagement can measure the RF characteristics and they can be added to the library. Once the library has been evaluated and the drawing has been evaluated, then each layer in the drawing is formatted, sometimes to the level of individual elements where the height and construction materials are assigned, so that an accurate three-dimensional model is created. In addition, variable objects like freestanding inventory can be created and placed into the model. The demonstration begins by showing these steps being performed. An original AutoCAD file may have hundreds of specific architectural layers. The RF engineer evaluates the original file to get an assessment of what the building and what the facility contains. Then, our extensive library of construction materials is reviewed, so the RF engineer is ready to select those construction materials that best represent the characteristics of the space. If there are materials at the site that are not in the library, then as a result of an on-site engagement we can measure and add those materials easily to the library. Next, the RF engineer specifies which construction materials will be used in the current model. The actual formatting process consists of selecting, one at a time, various layers in the architectural plan, evaluating the elements on those layers, and assigning or mapping RF characteristics from the partition library to the individual elements of the drawing. To create specific objects, for example a vat or a forklift, the different parts of the object are formatted with different heights. To create an obstruction in the space, in three-dimensional space, that has the reflectivity and attenuation characteristics that would be associated with the actual object. As the formatting continues, a three-dimensional representation of the space begins to take shape. Although in this demonstration we won't format all of the interior partitions, we will get to see the three-dimensional representation of the vats, conveyor belts and assembly systems, product on the conveyor belts, and the general interior shape of the building. Unlike an architect's model of a new house or construction site that looks exactly the way it would in the real world, the RF CAD model is a stylized view that conveys the RF characteristics of the space for the purposes of accurate modeling. Here, the conveyor belts and assembly lines are shown. In addition, there are variable elements that exist in the environment, like forklifts or freestanding inventory. These too can be created and modeled. The creation of a completely formatted floor plan is a time-consuming and detailed process where the RF engineer pays careful attention to the accurate creation of the three-dimensional space. Once this is done, then we have the luxury in the virtual environment of creating freestanding inventory, of placing inventory on racks, of moving objects and vehicles around in the space. So let's take a look at how we would create some freestanding inventory in the environment. This same type of process can be applied to simulating varying stock levels in a warehouse and varying the level of production in a production facility. This is something that you don't get with a typical on-site engagement where the measurements are made on the day that the on-site engagement takes place, and the facility may change the very next day. Once the three-dimensional model is complete, virtual access points are created and placed into the space. We have an extensive library of vendors' access points, and new ones can easily be added with a variety of antenna types. Here's the process. To create a new access point, we obtain the vendor's specifications for the radio equipment, and then using the software system, the access point or virtual access point is created. When it comes to antennas, we have a huge library of specific manufacturers' antenna types, and new antennas can be added based on the manufacturer's azimuth and elevation polar coordinate graphs. So an access point with a specific antenna is created and added to the library. Then the RF engineer places the access point into the model to start the predictive process. In real time, access points are moved and the associated propagation boundaries are evaluated to assure proper coverage. There are a number of predictive methods that are applied, including sophisticated, patented algorithms that are part of the RF CAD modeling and simulation system. One of these, ray tracing, is the process of evaluating reflections throughout the space. In addition, when path loss is calculated, it's not calculated simply by adding the gain and subtracting the attenuation, but rather sophisticated predictive models are applied. Several models are available for the RF engineer to select, as well as a variety of configuration parameters. Specifically, some of the important things are that the radio transmitter, the access point, could be placed 20 feet in the air, 30 feet in the air, 10 feet in the air. And because this is a three-dimensional prediction, the user's device, which might be 4 feet off the ground or 5 feet off the ground, or 20 feet if the user is on a rolling stairway, for example, in a warehouse environment, the three-dimensional relationship between transmitter and receiver is configured in the modeling process. The RF design engineer specifies the appropriate parameters and then begins the design with the antenna positioning mode. In this mode, the designer can move the access point around in real time, and here we see the red boundary representing the minus 82 dB milliwatt propagation boundary as the designer is moving the access point through the space, paying attention to where the signal will propagate. One thing you can see is that RF signals don't propagate in circles in an indoor environment. Maybe in outer space they do, but we see a number of times that designs are based on someone drawing circles on a floor plan, and you can see that that is not what the RF signal looks like. Right now the access point is 30 feet in the air, but it would be much easier to install if it were, say, 13 feet in the air and could be accessed from a ladder. So let's move the access point down to 13 feet above the floor and reevaluate by moving it around in the model space and seeing what the propagation looks like at 13 feet. We find that we can move the access point from one side of the support pillar to the other, and not a dramatic change occurs. So let's evaluate reflection from the metal objects in the space by performing a ray tracing model. The ray tracing model, which actually takes almost 15 minutes to generate in real time, provides a representation of signal reflection in 3 dimensions so that we get a very accurate representation of what the expected coverage pattern is going to be from the access point. So we'll ray trace in the specified area and see what the results are. We'll set this ray tracing model up to generate a total of 6 reflections from one object to another. As the model generates, a 3-dimensional representation of signal reflection is calculated. Again, in real time, this actually took almost 15 minutes. After the model is generated, the RF design engineer will first evaluate several graphs that represent the overall signal coverage in the space, and then the RF engineer will view the grid coverage and 3-dimensional grid coverage models showing the actual signal. What you can see is that signal has been reflected from the tall stainless steel tanks in a pattern that would be very unexpected if you were walking around at an on-site survey trying to identify these characteristics. This is one of the things that RF CAD modeling and simulation provides that can't be provided if a design is done based solely on a walk-around site survey. One of the places where weak areas or dead spots are often unanticipated are on the floor directly below an omnidirectional or dipole antenna. You see, a dipole antenna can be imagined to operate much like a fluorescent light tube. That is, the signal that comes out from the sides of the dipole antenna radiates outwards with a pattern that has no electromagnetic radiation out the ends. Therefore, there is essentially a weak or dead area that is directly below and underneath a dipole antenna. This only shows up when the antenna is mounted in a high location. Let's take a look. First, we'll move the antenna back to ceiling height. Now, when we zoom in, we can see that the antenna is raised above the floor. Next, we'll generate a grid coverage model for this antenna and see how there's a weak area directly below the dipole. We'll set the prediction distance at 1 foot off the floor to make the weak area most visible in the prediction diagram. One of the things about 3-dimensional modeling is that these types of considerations can be previewed at design time without having to come back later and discover that a problem exists. By looking at the legend on the left-hand side of the page, we can see that yellow at minus 65 dB milliwatts is a better coverage than the green areas at minus 70 or minus 75 dB milliwatts. And directly below the antenna, there's the green, weaker coverage area on the floor of the plant. When areas like this are observed in the predictive design, we might want to go on-site and more carefully pay attention to those specific areas in a large plant facility. Here, a three-dimensional grid coverage model makes it even more immediately evident that the coverage directly surrounding the access point is less than the coverage moving further away. Let's consider now what a user would perceive as they walked around on the plant floor underneath this access point and in the weak coverage zone. To do that, we'll generate a three-dimensional contour coverage model. In this model, we'll see the propagation boundary of the RF signal represented as a solid three-dimensional volume in space. When the model generates, we see the funnel-like shape in the center of the volume. This is the top of the antenna. To look at the user's view, we'll turn the entire three-dimensional model upside down so that we can look effectively up from the bottom of the floor, upside down of course, and see what the user would see. And that area is the area where there is less signal coverage on the floor surrounding the antenna that's on the ceiling. When considering the use of directional antennas in a facility, RF Predictive CAD modeling and simulation provides an excellent way to test various orientations and down tilt on the antenna to see what the predicted coverage patterns are going to be. In the example that we'll look at, the unexpected reflection characteristics from the walls and the stainless steel tanks in the environment produce a coverage pattern that was really unanticipated until it was seen in the predictive design. So as we begin to reorient and rotate the antenna, and you can see the antenna pattern graph in the upper right, and the corresponding propagation boundary moving in real time in the model, as we rotate the antenna, we look to see those orientations which will provide the most effective coverage based on the design parameter. As you can see, it would be almost impossible to guess or anticipate or accurately measure these types of propagation boundaries in a real-world environment. Once the correct orientation is determined, then contour coverages are laid in to mark the coverage boundaries. The red area denotes that zone in which a minus 62 dB milliwatt coverage will be obtained, yellow minus 72, and green minus 82, the limits of expected connectivity. We can also view this as a 3D contour coverage. Now you may have noticed that the directional antenna is pointing off to the left. A ray tracing model, which in this case took over 15 minutes to generate, shows that the anticipated coverage is actually occurring as a result of signal reflection from the wall and interior objects in the plant facility, so that the antenna, although it is not pointed directly into the space, is covering that area as a result of the reflection. In this case, coverage, but also interference and noise can be evaluated not only as a direct result of the source, but through reflections as well. Signal to noise, that is, how strong the signal is relative to background noise, and carrier to interference, how strong the desired signal is relative to all the other signals, are critical pieces for proper operation in a design. If the signal to noise or carrier to interference ratio is insufficient, it can be corrected through design modifications which can be tested in the simulation before configuration changes are made on site. In this way, potential problems can be identified, and if there is a need to further research them on site, then it's time to bring in a spectrum analyzer based on the findings of the virtual model. Now, in the model that we've created so far, both access points are on channel 1. So when we look at the relative contours, here's access point number 1, the propagation boundaries, and then we'll overlay the propagation boundaries for access point number 2. We see that they could interfere. Before we study the interference in detail, let's make sure that the signal is sufficiently above the noise floor by looking at the signal-to-noise ratio in the current design. We want to see a signal-to-noise ratio of at least 16 dB. The higher, the better. In this case, the yellow and orange indicate that the predicted signal-to-noise ratio will be greater than 34 dB, which is excellent. But now, when we look at the carrier-to-interference ratio, because both radios are configured on channel 1, we see that the blue and green highlights, this is an area where the carrier-to-interference ratio falls from 2 to -2 dB. And that's a bad thing. Well, not a problem though, because we simply have to create an appropriate channel plan. So we'll move one of the access points from channel 1 to channel 6, and that should correct the problem. With a simple reconfiguration in the RF CAD modeling and simulation system, we can move the access points easily and change any aspect of their configuration. In this way, configuration changes, just like physical location changes, can be simulated in the virtual space before going on site to actually do an installation or a configuration. So we move the access point from channel 1 to channel 6. And now let's redo the carrier to interference grid coverage model. Remember, before we had green and blue hues indicating that the carrier to interference ratio was 2 to -2 dB. This time, however, the carrier to interference ratio has gone up dramatically. We can see now yellow and red hues in the area that used to be blue and green. The yellow hued area is a carrier to interference ratio of greater than 34 dB. And since we're only looking for 16 dB for best case connectivity, we've created an appropriate channel plan. RF CAD modeling and simulation has at its heart the advantage of being able to introduce variable components into the virtual space. Here we're moving a forklift with some inventory across the floor of the plant. We can introduce additional inventory, we can change the height, and when we're talking about warehouse shelves, for example, we could simulate 100% inventory levels, 80%, 90%. We can put moving stairways and objects in the environment. This is something that a traditional on-site engagement can't do, because when the on-site team arrives, all they can measure is what's there on the day of the engagement. So first, let's look at the coverage and potential shadows from the signal from access point number 1. There, behind the obstruction, the green area indicates the shadow that would occur when the forklift had placed the inventory objects at that location. Well, let's see what happens from the signal coverage from access point number 2. Now the shadow has moved to the other side of the object. But when we turn all of the access points on, we can do something that's impossible in an on-site engagement, because during an on-site design effort, you can't have all the access points in all of their locations. So now we see that coverage is correct. RF CAD modeling and simulation to build a design for a production facility. In summary, first, your AutoCAD architectural plan is formatted to create a three-dimensional RF model. Into this model, Virtual access points are created as necessary and placed into their proposed locations. Once they're placed into the design, variable factors are simulated and an accurate coverage map is created. A number of sophisticated tests can be done to assure proper connectivity. The RF engineer has the luxury of moving things around, reconfiguring things in the virtual space. In this way, when weak coverage areas or areas of concerns are identified, they can then be focused on in an on-site engagement. But because of the accuracy of the CAD modeling, the correct configuration and best placement of the equipment is almost always identified in the model. We find that post-installation validation typically confirms accuracy to within plus or minus 3 dB or better, based on how accurate the AutoCAD drawings are. The results of the predictive RF CAD modeling and simulation work is then detailed in a complete report with justifications for the design, discussion of the RF issues, and a full set of installers' working plans. This is what we call the Sweet Spot Predictive Site Survey Report. Thank you for giving us the time to demonstrate RF CAD modeling for a production facility. If you have any questions, please don't hesitate to ask.